right. That's good. Good. Okay. Get started in just a second here. Okay. Showing up. Let's go to gallery view so I can see all you guys. Reagan, Ben, Lauren, Shelby, Stephen, Nathan, Jacob, Rockford, Trevor, Elizabeth, Daniel, Zane, Jonah, Dylan, Lauren, other Sam, or maybe just one of the Sams. Okay. Hello, back in the physics lab room here. Don't think I've been here with one of your classes in a while. I think I did a lab here last week for the other class, but not for you guys. Let's see. What do we got going on? I have your tests graded and I can give you some general feedback. I think I'm going to briefly say something maybe towards the end of the hour about one or two of the test questions that would be good. I think worthwhile to spend some group time talking about because enough people had issues with those parts. And then I'll get you guys your scores with some feedback comments as well that were kind of part of my thought process in deciding on, how many points you would earn or maybe miss for a particular issue. And of course, the test was about momentum and energy. I thought people did pretty well overall. The test average was, the test average was definitely higher by a noticeable amount for the class compared to our first or second tests. So I'm planning to send you guys each some emails with comments on Moodle. I think you can do a couple comments, but I'd like to do a little bit fuller comments than that really has space for. Well, okay, no, another person popped in. Okay. Okay. So let me see here. Let me bring up a couple of reminders to myself about that test. Wrong class. Just a moment. And I have really extensive comments, actually. Well, medium extensive. It takes a lot of space on an Excel spreadsheet, I guess. So the average on the test was out of 60. The average of the test was, where is it? Low 50s, quite good. 51 or so out of 60, that's 85%. And where is the test itself? Okay, I think I'll just briefly here share my screen and kind of point to the two problems that I think are most widely applicable to several of you in the class. And a little bit of a blast from the past here. People did great on number one. Number two was 6 points. It says that kind of right there. It was parts A, B, and C were about 2 each, and then part D was 1. So it was actually 2 for A, 2 for B, 1 for C, 1 for D, a total of 6. Of those 6, I think a really common score was like 3 out of 6 or 4 out of 6. And now here's the strange thing to me. People would consistently, I think absolutely everybody answered part D correctly. How far does the combined bob swing up after the collision? They start at 50 on either side, they swing down, smack together, and move to the right. Is it more than 50, exactly 50, or less than 50? A lot of people, I think everybody, said less than 50 degrees, which is correct for D. That means mechanical energy is not conserved somewhere along the way. If mechanical energy were conserved in A and B and C, you would start with two objects at this height, and you would maybe later on find both objects, back at that height, which means you could start at 50 degrees to right and left and end up with the combined object swinging 50 degrees to the right. So if you answered capital C less than 50 degrees for D, that is effectively, in my mind, the same as saying somewhere along the way mechanical energy was not conserved. That's not the only kind of answer people maybe, that's not the only issue in the problem. There's also questions about momentum, but somewhere along the way in A, B, and C, mechanical energy is not conserved. And that occurs during a perfectly inelastic collision in step B, kind of this middle panel. The two blobs hit and stick together. That's a perfectly inelastic collision. Collisions conserve momentum, so B conserves momentum. Perfectly inelastic, you lose kinetic energy, which means you lose mechanical energy. So the correct answer for B is momentum only. During the swings, changes in height that are nice and smooth with no friction or air resistance, changes in height like scenario A, downward swing, and scenario C, kind of upward swing, those conserve mechanical energy. So the correct answers are mechanical energy only for the downward swings, momentum only for the collision, mechanical energy only for the upward swing. The two swings are pretty much symmetric processes, so the answers are the same for A and C. So those are the correct answers. You need to understand the concepts both from a calculation standpoint, which of course comes up later on the test, but also from just being able to converse fluently and accurately about engineering concepts. So that might be a little bit more relevant to the front page of the test. Multiple choice, is momentum conserved or not? How can you tell? So that is something you really need to have a process for deciding. Honestly, if you can do the calculations in the next four problems, then a question like this should be really easy, because you would have to have done this step on the later calculation questions and then many, many more steps on those questions. Whereas here, you just have to decide, is momentum conserved? Yes or no. Is mechanical energy conserved? Yes or no. And then do it for a couple scenarios. I think people did pretty well on this one. Work is a scalar. You should include the sign, positive or negative, with the work. The correct answer is that gravity does zero work, normal force does zero work, friction does negative work, and the applied force in this case does positive work. A number of people wrote the right number here without the minus sign, and hopefully it was clear when you then did part B. Hopefully it was clear that whether you understood that the work done by friction is actually negative or positive. But if you used it as a negative in part B, that means you should have been listing it as a negative all along, okay? You don't decide whether to add or subtract the work. You always add the work, but sometimes the work's a negative number. When we talk about the charge of an electron, it's negative, right? The charge of an electron, it's measured in some units maybe you're not too familiar with, called coulombs. But if somebody asks you the charge of an electron and you say, if somebody asks me the charge of an electron and I say 1.60 times 10 to the minus 19 coulombs, that's not correct. Charge is a scalar, and the sign of the charge is pretty important. Protons and electrons, positively charged and negatively charged things, act differently. Positive work for the force and negative work for the friction, those are different. You really need to get in the habit of thinking about positive and negative signs. Some of you, the work you did in the test indicates you're not really in the habit of doing that. You need to be in that habit. Another problem where that would come up is this question. Heading to the east and heading to the west are not the same thing. If you did some work on number 4A or B or C, and you never anywhere distinguish between east and west in your math, then there's no way the math could be fully capturing this scenario it's trying to describe for you. I would recommend calling east positive and west negative. Some people did it the other way around and did perfectly fine. They called west positive and east negative. Um, all these answers could be positive or negative, which means they could be kind of east or west. Velocity is a vector, average force is a vector, average acceleration is a vector. Really quickly on 4B. Sedan, I know you haven't looked at this in a while. I just want to make some quick comments that you can maybe take into account and add to individual specific notes that'll be given to each of you, individually. Two things were head-on and they slammed together and they stuck together. One was a little bit bigger vehicle, an SUV, compared to the other one, a sedan. How should the force on the sedan compare to the force in the SUV? Before you get into detailed calculations, you should know after 30 seconds of thought how these two blanks are supposed to relate to one another. How are these two questions, force on sedan and force on SUV, ought to relate to one another? The force on the sedan is from the SUV. The force on the SUV is from the sedan. We call that an action-reaction pair often. By Newton's third law, these have to be equal in strength and opposite in direction. Now, knowing that, you can maybe go out and try to calculate one. But if your answers weren't equal and opposite forces, something should have been a little alarm bell going off in your head, because clearly a mistake crept in somewhere, because force of A on B is always equal in strength and opposite in direction to force of B on A. The accelerations are not equal in strength. Do you think, let's make it more extreme. Let's say it's not just a sedan and SUV. Let's say it's maybe a small car, a compact car, maybe replaces the sedan, and in place of the SUV, it's a bus. Do you think the experiences of the passengers in the compact car are the same as the experiences as the passengers in a bus when they hit, if they were to hit? Which do you think it might be safer and to be on? If you had to be on one of those vehicles when the collision took place, which one do you think you would want to be on to decrease your chances of getting injured or to decrease your chances of serious injury? The bigger the vehicle, the less it's going to accelerate when it interacts with something else. The bigger the object, the less it's going to accelerate. So the forces are equal in strength, directions are different, but the accelerations are definitely not equal in strength. They differ because one object is lighter than the other. So these should be the same. One's positive, one's negative. The sedan acceleration should be a big number, and the SUV acceleration should be a small number. If you could find any one of the four numbers for part B and part C, filling in the other three should go like snap, snap, snap. Now I'm going to bring up something very specific. A number of people had the same wrong work for C, which looked very weird to me. And a number of you had the same work. That should not be happening. I mean, that seems unlikely to me to happen. So I don't want to see that in the future. So in particular, some people had some numbers here that I think accelerations were like 8.33 and 5 or numbers like that. Those aren't the correct numbers, but those were some fairly common numbers people ended up with, which I found odd. When doing part B and part C, it's not enough to know that one car started at 35 meters per second and one car started at 25 meters per second. You also need to have basically already done part A and found the final velocities. But it's also not enough to just know the final velocities. We have to know things like change in velocity. And again, there's some habits that just aren't sinking in for some of you. VI, VF, and delta V are not the same. They're simply not the same. And if you're using the same symbol for all that stuff, it's probably going to lead to mistakes at some point, maybe on a question like 4B or 4C. Don't mean to be too critical. Like I said, the test average was solid and good and higher than the previous tests, and a good score. But there are some issues that by the latter parts of your freshman year as an engineering student, or by the third, second half, third month of a physics course, need to be habits that carry over regardless of the particular physics or engineering topic you're looking at. In fact, those habits are more important than the particular details that we're learning in this physics class, because those habits are going to continue to get used the rest of your career. What kind of habits do I have in mind? Paying attention to signs and directions, using proper units and always including units, thinking of basic principles first, and then doing calculations later, and then doing reasonable checks maybe based on those basic principles and intuition to see if your calculation is reasonable. Not going to say too much about this one. This is very much a vector question. It's definitely a collision question, but it's about two-dimensional motions. You need to be doing X's and Y's. Most people were doing X and Y calculations, maybe with a slight mistake, but pretty good, I think. I was pretty pleased with how that one went for all of, the 27 of you as a group. And the best, funnest question we have here. I think people did pretty well on this. I'm just going to say part F, I think, is a quite fun or interesting question. I graded it pretty lightly. It was only 2 points, and if you did something semi-reasonable, you probably got a point. If you did it all correctly or nearly correctly, you got 2 out of 2. So not a really big effect on anyone's score, but I think an interesting question to think through. I'm going to write down briefly on the board the answer to part A, initial mechanical energy of the block. Most people got that right. And the answer to part B, work done by friction when the block crosses the rough patch. Part B, most people got that right. Actually, I'm going to write 2 things about friction. I think I'm going to say E initial, and I'll zoom in there, I think. And the answer is 17.82. If you wanted to round that off and use different significant digits, that's fine. I'm going to write it just that way because I remember that number. Okay, and then that's a combination of kinetic energy and potential energy. It was in motion with kinetic energy down the hill, but it's starting high on the hill, so it's got potential as well. People got that right. I'm going to write 2 numbers here. The force of friction was given in the problem, 2.94 newtons. And the work done by, I'm going to say something like against the motion. Why am I going to say that? Because force is a vector and kind of has a direction. You guys know the direction, I think, pretty well. What's the work done by friction? You take this and you multiply by the distance, the width or the distance traveled to cross the rough patch, which is 0.6 meters. And then you multiply by cosine of 180, or in general, you get a minus sign. So this, again, this should be negative 1.764 joules. So this is the intended answer for part B. I'm just going to mention that one in passing. And that's the intended answer for part A. Okay. Let's try to think about part F. Part F can be done, honestly, you can do part F in 30 seconds. It's not a long calculation. It doesn't need to be a long calculation. You don't have to have done C, D, or E in order to answer F. You could do them along the way, and that could help you, but you could just jump to F and just answer it pretty directly. Here's one way to do it. Every time we cross the rough patch, we lose 1.764 joules of energy, and we started with 17.82 joules of energy. So, so if you guys can see that there, I should have done that. You lose that. So here I'm just going to write some numbers sorry, I'm going to show you Desmos calculator screen. I'm going to do this. Let's go to, where's the net? There it is. It's not your class. Okay, let's go to desmos.com. Whoop. And then I'm going to grab the scientific calculator just to kind of put some numbers on the screen. Here's what I'm going to do. 17.82 answer. And then I'm going to do answer minus, I'm going to almost say plus, negative 1.764. So basically going to be subtracting 1.764, right? And I'm just going to highlight this and do this a couple more times. So after you cross the rough patch once, your energy has dropped to 16 or so. And then it drops to 14 after the second pass, 12.5 after 3 passes, 4 passes, 5 passes across the rough patch, 6, 7, 8, 9, 10, 11. Oh, wait, my energy went negative. So you can cross the rough patch this many times, and if you count, I think that's 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and you still have a positive energy, but we're not going to be able to have a negative energy because kinetic energy is either 0 or positive. Potential energy of a spring is either 0 or positive. And potential energy of gravity is lowest when you're at the lowest point, and the rough patch is at the lowest point. So we're measuring from height 0 basically. So we can't have any of the 3 energy types go below 0, so the total can't. So after crossing it 10 times, how much energy do you have left? 0.18 joules. So you go back and forth 10 times, and then on the 11th attempt, you don't make it the whole way. You only have enough energy to go how far? You only come in with 0.18 joules. And you could do this a couple ways. You could find what fraction that is of the work of the energy needed to cross the patch and then multiply by 0.60. So we could do that. We could kind of do something like this. What fraction of the patch can you cross if you have 0.18 joules of energy? Well, you need 1.764 joules. So you can only cross about 10% of the patch. How long is the patch? 0.60. Oh, I missed something. Answer. That's what I missed. 10%. This number is dimensionless because it's joules over joules. 0.18 joules over 1.764 joules. You can make it a little over 10% of the way across the patch, which means a little over 6 centimeters. So the resting place ends up being about 6 centimeters to the right of the far left edge. Here's another really quick way to do it. How much energy did you start with? And what is the formula for work? Work is change in energy. Eventually, the change in energy is going to be, we're going to lose all the energy. So eventually, our change in energy will be negative 17.82 joules to end us at 0. What's the force of friction? 2.94. So if you have 17.82 joules of energy, that's enough energy to cross what total stretch of rough terrain? It's enough energy. This is like work over force is distance. You have enough energy to cross how much rough terrain? A little over 6.06 meters of rough terrain. Well, if you have a 0.6 meter rough patch, that's going to be enough to cross it 10 times. See that? Like total distance is a little over 6 meters. Well, 10 times 0.6 is 6 meters. So you cross it 10 full times and an extra 0.06 centimeters. And there's the same number as I think written right there. It's written right there, but in this case, maybe we just did it as like kind of 2 calculations. Part A divided by force of friction is a total distance, and then consider how that compares to number of crossings of the rough patch, and you get an extra 6 centimeters beyond 10 full crossings. And that is for this guy. That's for this guy. Does the incline affect part F where it eventually will stop? If it's a frictionless incline, a frictionless surface here, a frictionless surface here, and a nice spring here, none of those issues will affect where it stops. It might affect how long it takes to rise the hill and descend the hill. It might affect when it stops. In fact, I think the spring will affect when the object stops, and the steepness of the hill and details about the hill probably will affect, like the shape of the hill, probably will affect when the object ends up coming to rest right here. But it's going to come to rest at this spot about where my cursor is, 6 centimeters from the left of the edge, left edge of the rough patch, regardless of the conservative forces in the problem. Only due to the non-conservative forces in the problem, which are normal force, which throughout the problem does 0 work, and friction, which is, of course, described as 2.94 newtons only over a certain patch of ground. Again, all that was for just 1 or 2 points for F, but I think that's kind of a fun question, and maybe an example of trying to bring together all these ideas: work, kinetic energy, potential energy of gravity, potential energy of a spring. Some people did some parts of number 6, or maybe also some parts of, which other question? Number 3B, by using equations of constant acceleration, things like position is 1/2 at squared plus v naught t plus x naught, things like that. You can do that on some of these problems, but usually it's more time consuming, and I think then it would be to use an energy approach or a momentum approach, in particular an energy approach for 3A and 3B, and then energy approaches for that whole ramp, rough patch, spring number 6. So a couple thoughts there. Yeah, I think I don't want to show that other thing quite yet. So a couple thoughts there. We're now going to start talking about oscillatory motion, having just talked about orbits and gravity and, you know, potential energy of gravity and force of gravity between the Earth and satellites, for example. We're now going to talk some about simple harmonic motion. So for the next half hour, I'm going to kind of go over the basics, which almost all the basics we've already seen. Most of them we've already seen once or twice, and we're just going to kind of bring them all together and focus on them as a set of concepts. And I'm then going to talk about we have 2 or 3 kind of favorite examples of what we call simple harmonic motion. Simple harmonic motion is going to be our kind of go-to title or phrase for an object that is oscillating back and forth in a nice smooth way between kind of 2 turnaround points. Not everything that oscillates is following simple harmonic motion, because simple harmonic motion is a very detailed, precise term. Just like not everything that goes up and turns around is a parabola, but we talk a lot about parabolic motion. You know, not everything that goes back and forth between 2 turnarounds is perfect simple harmonic motion. What are our favorite examples of simple harmonic motion? A mass on a spring. That is our favorite go-to example. Any mass on any spring. A horizontal spring where it's kind of bobbing this way, simple harmonic motion. A vertical spring suspended maybe from the ceiling, bobbing this way, simple harmonic motion. A mass on a spring on a ramp, maybe it's kind of on a little kind of incline. Maybe imagine a ramp right here. That would be simple harmonic motion. Even put the mass on the spring in the middle of outer space, pull the mass over and let it go, and it'll start bobbing. Simple harmonic motion. What's our next favorite example? Our next most common example? A pendulum. And one thing you need to understand by the end of this week is how a pendulum is not actually perfect simple harmonic motion. A spring is, and it's our kind of canonical example of what we mean by this type of motion. And a pendulum is close to simple harmonic motion in some scenarios, but if you do certain other things with a pendulum, especially if you take the pendulum and you swing it over like very, very far, if you swing it over a little bit, this is pretty good simple harmonic motion. But if I swing it over really far, this isn't quite so good of good example of simple harmonic motion. And the further over you pull it, the less accurately it follows what we're going to talk about today. So here's second. I'm going to zoom in here, zoom out, sorry. I'm going to erase this, and I'm going to put up 4 bubbles, and there's going to be kind of 4 facts that are very important facts about simple harmonic motion, and they kind of are interchangeable. Like if one's true, the others are true. If one's not true, the others aren't quite true. So imagine this is our scenario. I'm going to say SHM. And our favorite example is a mass on a spring. A mass M attached to a spring, and we describe a spring with a K value. So what's the spring constant K? What's the mass of the object M? I wanted to put a diagram. Okay, I think I'll draw the diagram in a little bit because I want to get these four concepts on the board first. So here are 4 interchangeable ways to think about simple harmonic motion. Let's say the question is, you're looking at an object moving back and forth, and you're wondering, is that perfect simple harmonic motion, yes or no? Here are 4 different things you could investigate to determine whether it is exactly simple harmonic motion or not quite. So I think I'm going to say these are in not really any particular order, but there is a fact about force. Oh, what am I doing? There's a fact about force. There's a fact about potential energy. I'll just say PE, potential energy. If you check the force fact, you can find out whether it's simple harmonic motion or not. You can check the PE fact. There's a fact about the motion of the object. Like if you look at its motion, so I'm thinking of this would be an equation for like F. This would be an equation for U. This would be an equation for X, the position. And then I'm going to say those should seem like pretty common things for us to talk about. Positions in meters, forces in newtons, energies, in this case potential energy measured in joules. And then a 4th thing we're going to talk about, which is pretty specific, is period. If you're watching something move back and forth, it has a period. And you could look at the period, take measurements on the period, or investigate the period and find out if you have simple harmonic motion or not. Guess what the force law is? Very easy if you know what the equation for a spring is. The force law is Hooke's law. And I'm going to say it in words, and I'm going to say it as an equation. Okay, it's mainly on there, right? The force, here's what I would say about the force. If you have simple harmonic motion, you have a linear restoring force. What's the equation? Hooke's law. So if the net force, and when I say force, I mean net force. So I'm not going to write net. I mean, I wrote it, I'm going to erase it. But if I ever say force, I mean the net force. Usually we'll have pretty simple free body diagrams in this unit. The pendulum free body diagram will get a little more interesting. The spring free body diagram will often be a diagram with just one force, the spring force. And what's the equation for the force of a spring? Negative Kx. You could say negative Ks or something like that. I'm going to use X for most of this unit to mean the direction the spring is oscillating. Okay. Which part of this is the linear? x to the first power, which part of this means restoring? The negative sign. What should the potential energy be like to be a big thumbs up for simple harmonic motion? This should be a parabolic graph. So what should the force graph look like? If you did a graph of force versus position, here's the description in words, here's the equation, here's a little sketch. It should be a straight line downhill through the origin. So this is, to the right is x, and up is force. If you look at a force versus position graph and you see this behavior, you've got yourself simple harmonic motion. Okay? Straight line with a negative slope through the origin. Parabolic. If you look at a graph of potential energy compared to x, don't expect straight lines. You want to see, is it a parabola? What's the equation for the potential energy of a spring? This is the equation for the force in a spring. What's the potential energy? 1/2 kx squared. So the equation here would be U equals 1/2 kx squared. And then the motion. Guess what you would get if you made a graph of x is now vertical and time is horizontal? What do you think the position time graph looks like for an object that's, you know, doing this? If you just move time along, instead of doing this, am I on the screen just barely? Instead of, if you did this and then you just kind of walked with it, what kind of shape would I be drawing out? Instead of going just up and down and up and down and up and down and up and down, I go up and I go down and I go up and I go down and I get a big parabola. Sorry, I get a big sine wave, excuse me, a sine wave. And I don't care if you call it a cosine wave or a sine wave, you get a wave. So the motion would be sinusoidal. Sinusoidal, sines and cosines. Oh, that's right. Let me grab one textbook. Sines and cosines is what I was saying. And then I'll write some stuff in there. Our go-to is probably going to be to use cosine for a wave, but it doesn't really matter deep down if you use sine or cosine, but you should probably know that in our textbook, they usually would write the equation as x equals a cosine t, cosine ft. So here we go. The motion would often be, I'm just typing this in the chat, sinusoidal motion equation would be often x equals a times cosine of, here's a couple ways, there's many different ways you could write this. I would say to write it like this, 2 pi over capital T times little t. And what do you think I mean by capital T and little t? Capital T is a time constant called period, where A equals amplitude, and capital T is period. Little t is the variable representing how long you wait. You know, is it 2 seconds after it started bobbing? Plug in little t is 2. But the period is representative of the system. You know, like which mass did you choose? Which spring did you choose? If you choose a different mass or a different spring, you get a different period, capital T. choosing a different mass or spring doesn't have a big effect on the amplitude. You could have a small amplitude with one spring or a big amplitude with one spring. So that's going to be kind of our go-to. And we could just check and see if some of this stuff works together. I'm going to do a little bit of calculus here in a little bit to figure out how K, what's the formula for capital T? Or how does K affect capital T? How does spring constant affect time to oscillate? And so basically, I'm going to come up with that equation over there in just a little bit here. But I'm going to say in words the key idea for the period. Here's the key idea for the period. Ready? In simple harmonic motion, the period is independent of the amplitude. The period is related to something like K of the spring, but the amplitude's not, and the period does not depend on the amplitude or vice versa. So the period is independent of the amplitude. So I'm just going to write that in the chat actually. In SHM, the period is independent of the amplitude. That is a very, very important statement. And mathematically, it's going to show up because when I write the formula for capital T in that bubble, capital A won't be in the formula. Other stuff will be, but not capital A. The period is independent of the amplitude. So I'll say like this, the formula for T, capital T, does not include the amplitude A. That's what I'm going to say, double checking. So what does that mean about a pendulum? Now I'm going to shift from spring to pendulum, maybe because it's a little more visual. What does it mean about a pendulum? It means that if the pendulum is simple harmonic motion, swings that are this big take just as long as swings that are this big. If that's true, then the pendulum is probably obeying simple harmonic motion, and all these other facts are true as well. If that's not true for the pendulum, then it's probably not quite perfectly simple harmonic motion, and all these other facts are going to be not quite perfect. If the period changes a little bit with the amplitude, then your graph is not going to be quite a straight line. Your graph of potential energy is not going to be quite parabolic, but it might be close. It might look like a parabola from a distance, but you get up close and you're going to notice it's not quite a parabola. And your graph of the position will go up and down perhaps, but it won't be a perfect sinusoidal kind of cosine wave. And I think we have enough on the board to figure this out. How could we come up with a formula for capital T? Actually, we've already got enough equations written down. I think I'm going to focus on the one that I wrote for the motion equation in the chat. I think I'm going to erase this, going to write the motion equation and the force equation. And then what other fact do we need to relate motion to force? What does Newton's laws of motion say about force? It's not equal to m times position. It's not equal to m times velocity. It's equal to m times acceleration, right? Well, if I have an x formula, and I do have an x formula, x equals capital A cosine 2 pi over capital T little t, I can take a derivative and get a velocity formula. I can take another derivative, get an acceleration formula. I can multiply the acceleration times mass and get a force formula. And then I can set the force formula equal to negative kx and see if I learn anything that I didn't already know. So that's what we're going to do here in the next couple minutes. First up, I'm just going to make sure we're all on the same page about some meaning of these terms. Where's the web? Simple harmonic motion. Okay. Can you guys see that sine wave on the screen? It's part of my screen's covered. Okay. So here's 3 or 4 key pieces of information about a sine wave. most importantly would be capital A and capital T. And I would say of the two, capital T is the most important one here. I'm going to, I don't know why I called it E. Why did I call that E? Equilibrium. That's why I called it E. Equilibrium. What's the equilibrium point of this wave right now? The peaks are a little higher than the troughs are compared to the midline x-axis, horizontal axis. So the midline is actually right there. And if I move E around, if I move the equilibrium around, I'm doing this. So this is simple harmonic motion about 0.31, and this is simple harmonic motion about 0.16, and this is simple harmonic motion around negative 0.48. But you notice the shape is the same. So that is not a really big deal to me. We need to know where equilibrium is, but usually we kind of center our thinking there. So what does equilibrium mean? Equilibrium is the point on this graph where the force is 0. Now on this graph, it's at 0, 0, but on this graph, it doesn't happen at x equals 0. The force apparently is equal to 0 at this dotted line of 0.16 meters. So I'm going to just put that down to 0 because that's the least important one. So I just mentioned it briefly at the outset, it's least important. What's period? This is period, right? This is period, and this is amplitude. Whoa, what am I doing? This is amplitude. Let me put this at 8, just kind of a nice number. 6.5, 6. Okay, couple things. Oh, that's the amplitude, right? That's the amplitude. And that's this number that I'm adjusting right here, okay? Amplitude is middle to top, not bottom to top. So amplitude is 0.55, and overall this is traveling up 1.1 meters. Let me put it at 0.5. Overall, this is traveling up 1 meter, down 1 meter, up 1 meter, down 1 meter, but the amplitude's a half. What's the period? I think you guys should know this. We're just kind of reviewing. The period would be kind of shown. Oh, sorry, I didn't mean to do those. That's what I meant to do. That is the period, right? So the red is amplitude, the blue is period. Let's increase the period. And there we go, we're increasing it. And maybe we're going to take the red ones off. One full period can be split into 4 nice equal pieces. How far does the object move in 1/4 of a period? Period is the time from being at one point on the wave to being back at the exact same point on the wave the next time. So period is, let's say, peak to peak. Here's 4 key moments, or 4 key chunks, and I'll make the period a little bigger. Uh-oh, I took one away. What happened? Okay, accidentally deleted one. Let's make the period bigger. Okay. How far do you travel in the first quarter of a period? Peak to 0 in a quarter of a wave, in a quarter of a period. 0 to trough, quarter of a wave. Trough to 0, quarter of a wave. 0 to peak, quarter of a wave. So capital T is this big distance, but if you divide T into fourths, 1/4 T, 1/4 T, 1/4 T, 1/4 T, that's kind of a fairly important time in some of these problems as well, because you know that's how long it takes to travel from one extreme to the equilibrium. And a full cycle is to do that 4 times. Peak to middle, middle to trough, trough to middle, middle to peak. And I think that's pretty good. We're going to do this. And now we're going to do some calculus, and we're going to come up with a formula for capital T. What features of the system, I'm going to erase some of the stuff and kind of draw the system. What features of the system do you think affect how long it takes the spring to bounce? I'm going to go to our standard example, mass on a spring written in black at the top. You should definitely be thinking of the Hooke's Law lab. It's been a while since we did the Hooke's Law lab. but we did a lot of measurements about positions and mass and force. It was mainly about F equals negative kx, but if you remember in that lab, you also were asked to, just a second, are you guys still there? Okay. Mass attached to a spring. So the picture would look like this. Imagine this is a very strongly anchored wall, and then we just have a spring attached to a block. The block has mass m, the spring has spring constant k. I could draw a floor here, but I just want you to kind of imagine this guy is oscillating back and forth. Maybe he's going from like here to here, and he's kind of oscillating back and forth. And if you want to have a surface, a floor, just have it, imagine it being a frictionless floor. So because it's a frictionless floor, there's only one horizontal force acting on the mass. So I'm going to say a horizontal spring. I'm going to call this this is going to be my go-to meaning for a horizontal spring. A horizontal spring on a frictionless surface. What's the only force acting on the spring? Let's say that the dotted line is the equilibrium position. What's the only force acting on the spring? Acting on the mass. The force of the spring, which we know is kx. So this is F. This is x this way, but the force on, when you pull the spring to the right with a rightward x displacement vector, it provides a leftward force. So this is negative kx. And you can take the vectors off and make it one-dimensional, but that's correct as a vector equation. When you stretch the spring to the right, it responds with leftward forces on the mass. If you squeeze the spring to the left, that would be a negative x. It responds with positive forces to the right on the mass. Okay, let's do this. Can you see that pretty well? I would like to go from the x equation that I wrote on the chat to a velocity equation, to an acceleration equation, to a force equation, and set the force equation equal to this. I'm going to need most of the space, so I'm taking away what I just wrote, but I would, maybe add some more detail to that sketch as we go along. So here we go, position. The claim is that when you go between those four bubbles, if one bubble's doing what it says it's supposed to do, the other four are as well. So right now, I'm going to make the link between the motion bubble being a sine wave and the force bubble being negative kx. Let's go position. I would like to have an equation for position, like x of t. And then what's that? Capital A times cosine 2 pi over capital T times little t. What are the variables? A is a constant, 2 pi is a constant, capital T is a constant. The variables are position and time. All right, so you guys are all pretty good at calculus. If that's the position equation, what's the velocity equation? And maybe I'll do the velocity equation in blue. How do you go from here to here? You take a derivative with respect to little t. I don't know if this is off the screen. I think it's a little off screen. Derivative with respect to time little t. It's probably not quite on there. It's almost on there, looks like. Okay, everybody take that derivative. And we're going to get some stuff like that. We're going to get a factor of 2 pi over t, which is an important factor. That we'll get a factor of 2 pi over t that'll pop out. What's the derivative of cosine? Yeah, you still get something sinusoidal, but if the position was described by a cosine function, the velocity will be described not by a cosine, but a sine function. In fact, it'll have picked up a minus sign along the way. It'll be a negative sign. So I'm going to write it like this. I'm going to have some stuff out front, and then like sine or cosine. In this case, cosine. In this case, it's going to be sine. And the stuff inside of the cosine and the stuff inside of the sine is never going to change. The stuff outside will change, and whether it's cosine or sine might change, it will change. Here's t, here's 2 pi over capital T. And what's this? What's the coefficient now? You picked up a minus sign and a 2 pi over t. So it is negative 2 pi a over t. So quick example. I'm going to give you an amplitude and a period. Amplitude A equals 0.20 meters. And period capital T equals 0.80, well, no, that's right. 1.20 seconds. Okay. So we're going to imagine a mass bobbing back and forth. If you want to picture a pendulum, you probably can. Mass on a spring is a little better thing to picture, but either way is pretty good at this point. It's going 0.2 to the right, 0.2 to the left, 0.2 to the right, 0.2 to the left. And how long does it take to go from here back to here? 1.2 seconds. 1.2 seconds. Here's the question we can already answer with what we have on the board. What is the maximum velocity of the object? As it oscillates from here to here, what's the fastest it's ever going? Question is, what is V max? Well, you take the position equation, you take a derivative, and now we have a velocity equation. What's the biggest that this is ever going to be? What's the maximum of a sine function? Sine maxes out at 1 and -1. I mean, the max is 1 and the min is -1, right? So the coefficient out here is basically, this is the amplitude of the position, is called amplitude. It's measured in meters. What is the amplitude, or what are the extreme values of the velocity? Not a over t, which would have units of velocity. It's actually 2 pi a over t. So the max velocity is the number out front. Yeah, we got the derivative and basically set equal to 0 and do it. But you know, if you just picture if you picture graphing the blue guy, you're going to have a velocity wave as well. Position is one wave, velocity is also a wave. They have the same period, capital T, because the stuff inside cosine and the stuff inside sine is identical, but they have different coefficients out front. So Vmax is that coefficient out front. Vmax is 2 pi times A over capital T. And for the numbers given up above, 2 pi times 0.20 meters divided by 1.20 seconds. And I got 1.05 meters per second. I'm actually going to kind of call it plus or minus. Of course, the maximum is a positive, but I mean the extreme values of the velocity are positive 1.5 and negative 1.5. Now, when in the motion is it going fastest? 0 at a turnaround, speeding up fast to the left, 0 at a turnaround, speeding up fast, slowing down, 0, speeding up max. So where is the velocity at a peak? Vmax occurs at equilibrium, which means x equals 0. Equilibrium x equals 0. You could say plus or minus Vmax occurs there, which is basically a way of saying when cosine is at a peak, sine is near 0, and vice versa. If a sine wave, or in this case, a negative sine wave, let me say the other way around. If cosine's near 0, negative sine will be near an extreme value. It'll be near one of its biggest values, either positive or negative. Okay, what are we going to do next? Let's take another derivative because we need to get to acceleration. Why do we need to get to acceleration? We want to get to force, and force is mass times acceleration. So take another derivative, and then right after that, we're going to multiply by mass. Acceleration. I don't know if you guys can see that one very well. Maybe I'll go back to red. Acceleration. Okay. All right. What's the derivative of sine? Positive cosine, so this negative sign will stay a negative. The sine pops back to be a cosine. The inside of the cosine and the sine is never going to change. And what's this coefficient here? We get another factor of 2 pi over t from the chain rule derivative step. The derivative of sine is cosine, but you have to multiply by the derivative of the argument of sine, and the derivative of a constant times little t is just the constant. So now we get 4 pi squared a over t squared. Anybody agree, disagree? I think that looks pretty good to me. Okay, and now really quickly in the next 2 minutes, what are we going to do now? We're going to get force. Well, I don't have to do a whole lot to get force. What do I do to acceleration to get force? I multiply by little m. Okay, and I think I'm going to erase and write that up above. Okay, so what's force? MA. So it's just this times an m. Force has a negative sign. 4 pi squared m a over t times cosine. What do you notice about force, acceleration, and position? They're all cosines, right? Now, velocity wasn't a cosine, velocity was a sine, but these are all cosines. What's supposed to be true about these two for simple harmonic motion? How is force supposed to relate to position? It's supposed to be negative kx. Is that true? Is the force a negative sign times a constant times the position? They both got the cosines, they both got the capital A's. Here's the minus sign. Where did the minus sign come from? One of the derivatives gave us a minus sign, the other one didn't. So overall, in doing two derivatives to get from position, click, to acceleration, we picked up a minus sign overall. So we got the minus sign from Hooke's law. And then where's x? Well, here's x. All of this is x, right? So what's k? K is 4 pi squared m over capital, oh, that's a t squared. I missed a t squared. Okay, and you see what we're going for here? We're getting an equation that relates k, m, and t squared. And what's the equation? K equals 4 pi squared m over t squared. K is intrinsically positive, m is intrinsically positive, t is intrinsically positive, plus it got squared. Everything's positive of the constants. And here we go. In order for the blue to be true, I mean, the blue seems to be true, and what's playing the role of K? I'll write it here, solve for K, and I'm going to write it again, solve for T, because the more common way to write this formula is to solve it for T. 4 pi squared over T squared times M. Does that look about right? And I'm just going to solve that for T. What if you solve that for T? Maybe multiply T squared to the other side, divide by K, and then take a square root. When you take the square root of T squared, you get T. When you take the square root of 4, you get a 2. When you take the square root of pi squared, you get back to pi. So this is a very important formula, usually written this way, but of course these are saying the same thing. Is the period independent of the amplitude? Oh, sorry if that's a little bit high off the screen. Here's the formula. It's definitely in the book. 2 times pi times the square root of m divided by k. Mass m and spring constant k determine the period t to oscillate once. And that's the equation, 2 pi squared of m over k. What letter isn't showing up there? I know that might be a little frustrating. What letter is not in the formula for capital T? Amplitude. So force is negative kx. Position, which was written and I erased, but you got it in your notes, is the sinusoidal function. And then you get this for the period fact. And then how do you get the potential energy fact? We already know how to integrate forces and get potential energies. And if you integrate the force negative kx, you will get, you integrate and you take you multiply by -1, you get the 1/2 kx squared, which I think you guys are used to. So those 4 things hang together. If one's perfectly true, they're all perfectly true. It turns out for springs, they're perfectly true. For pendulums, they're nearly all true. So there we go. It's kind of like thinking to yourself, can you think of a function, think of a math quiz, can you think of a function that you can take 2 derivatives of to almost get back the exact same function you started with? But we don't want to get back exactly the same function, x. We want to get back negative times x. And if there's a constant, we're okay with there being a constant. We'll call it the spring constant. So what can you take the derivative of twice to get back almost the exact same function you started with? Sines and cosines give you a shot at that. In particular, if you don't want to get back the original function, if you want to get back -1 times the original function, sine or cosine, let's say cosine, does that pretty well. Okay, I'm going to let it go. By the way, this number right here is the maximum acceleration. Maybe ignore the minus sign, just this number here. The maximum position is a. The maximum velocity is 2 pi over capital T times a. And the maximum acceleration is 2 pi squared over T squared times a. Something to think about. We'll be using those facts quite a bit. Force and acceleration are nearly interchangeable. You just multiply or divide by mass. Okay, I think that should help you kind of get started on this week's homework, and I'll be getting you some information about your test scores and some comments, feedback for that today or tomorrow. Somebody just asked me a test question in the other test that I'm giving today. That's a little distracted because people are asking me test questions. All right, I've gone over by a couple minutes. Sorry about that. Have a good couple days. You can start trying some chapter 14 homework problems, I believe. Excuse me. Gallery view. both. Oh. Oh.
Hey, Professor. I had a quick question on the lab.
Yeah, what was the lab? Oh,
It was the balance table.
yeah, gotcha.
So when calculating torque uncertainty, like for each mass,
Yeah,
so I have the equation of like mass times like 9.8 times the like decimal uncertainty over the torque net. Are we using
say it
like
again. Just say it again.
mass times 9.8
Yep.
times like the 2.5 or 0.5 and then over
It's not
like
over anything. Just stop right there. Just it. It's just mass times 9.8 times either 0.25. What was it? 0.25 centimeters or times 0.50 centimeters.
oh, okay, then I just wrote down the equation wrong.
Yeah.
I was just
Um,
getting really big numbers and I was like, that doesn't seem right.
Yeah. I mean, it should mimic the what? How did you calculate the torques? This is the uncertainty in the torque. How did you calculate the torques?
I just did mass times g times x or
Yeah,
y. Yeah.
right. And what are we going to do for uncertainty? Mass times g times uncertainty in position.
Okay.
Yeah, and that'll give you the right units for torque.
Okay.
So actually, the like the numbers for uncertainty and torque are really repetitive throughout the lab because you're always doing either 0.25 meters, there's 0.25 centimeters, or you're doing 0.50 centimeters. So some of those numbers kind of show up on several tables. Oh, here we go again. It's another 100-gram mass, and it's another 0.25 meters for uncertainty, and you get the same torque uncertainty as maybe you got in a previous table.
Okay.
Yeah.
And then so would the UNC torque be like just all of those uncertainties added together?
Yeah.
Okay.
Like we didn't we have a little bit of uncertainty because we probably didn't put the first mass perfectly on the table where we said we did. Then we have a little bit more because we probably didn't put the second one perfectly where we said we did. So all those little bit of all those slight uncertainties kind of just combine.
Okay.
Yeah.
Thank you.
Yeah. Sounds good.
All right.
Professor Feig.
Oh, yeah, Jack. Hi.
Hey, so I don't know if you saw my email from
I
last
saw.
night.
I don't think I saw one a couple weeks ago, but I did
Yeah,
see one
okay.
this morning. But I didn't really get to read it very thoroughly. So
Okay.
yeah, I mean, I got the basic idea, but I was kind of doing other things. So yeah, go ahead.
Yeah. Okay, I was just, wondering like
Yeah.
if there is like any possibility for like an extension on last week's at least. Like I don't
Certainly.
I'd
Yeah.
be fine with not getting any points for 2 weeks ago lab and homework, but like at least like last week's lab and homework I could get done by like tomorrow night or Wednesday.
Yeah. I think you should still be able to submit it to Moodle. I think, I'll have a note when I go there. It'll say like when it was submitted and I'll see that. But I, if I set the assignments up the way I believe I did, I think you'd still be able to submit it. So if you were to do that, you certainly can. And I'll just, I'll see when I go to Moodle when it was actually handed in, and I'll know in the case of you, kind of what the circumstances have been for you, and that's fine.
Okay. All right, thank you.
Yeah. Yeah. When did that kind of start going for you? You don't have to tell me if you don't want to, but like, when did,
Yeah, it
I wasn't sure
started
like
on
when exactly this started to be such a,
started on
you know,
Thursday when I went to work. Um, it was just like really bad, and I was able to make it through my shift,
like,
but then after I got
like
back,
a
it
week
was
and a half ago Thursday or,
yeah, week
oh,
and a
okay.
half ago Thursday.
Okay. Yeah.
So after that, I've been missing work, and everyone's mad at me, and
Huh.
I've been late on a whole bunch of
Okay.
stuff. So
Okay.
yeah,
So a couple days before Easter, maybe. Yeah.
yeah.
Just think back. Where do you work?
I work at a gas station.
Oh,
We're always understaffed and it's
Yeah.
a mess. So
yeah. I
Yeah.
believe that. I believe that. All right.
all right,
Well,
thank you.
yeah, if you got questions, ask, but that's fine.
Yeah. All right, bye.
Yeah.